And I just deleted the drawing so we could see this. Well, anyway, yeah, I wasn't recording then. Here, they're just kind of averaging the formal charges, minus 1/2 from this, minus 1/2. These are the net negative charge, formal charge there. Yeah, so I missed the recording, unfortunately. Let's see if somebody did it here. I want a video. Here, there's a problem with this one. There's no net charge. There's no formal charge. So they wrote the square brackets, but it's still wrong. There's no net charge. And the oxygen geometry is wrong. This geometry is okay. This oxygen geometry is okay. You know, they just aren't showing the lone pairs. Okay, this is carbonate. Carbonate doesn't have a hydrogen here. There are actually 3 resonance forms for carbonate, for the position of the double bond, but we're doing bicarbonate, and there are only 2 resonance forms for bicarbonate. And so that's it. Any others? Here are the 2 resonance for bicarbonate. Here they aren't getting the, you know, this looks like a 90-degree bond. It's not a 90-degree bond here. This one looks okay, the shape of this one. Here, they're writing the net charge, the formal charge. Here, they're just writing the formal charge. So they don't have square brackets here. This is ammonium bicarbonate. They don't have square brackets, but that's okay as long as they have the formal charge shown here. Here, this is not good. This is wrong because they're not showing the formal charge and they're not showing the net charge, but they are showing 2 resonance forms. In this case, they put the hydrogen on the left. It doesn't matter where you put the hydrogen, but once you pick a position, you could put it on the left, you could put it on the right, or you could put it on the top, but never move it. Once you pick a position for the hydrogen, leave it there. Don't move the hydrogen. Here we can see carbonate. Carbonate's gonna have 3 resonance forms because we could put the double bond top, left, or right. I don't know what they're doing. No, they're just showing reactions here. This is carbonic acid. Carbonic acid has no resonance forms. There's only 1 position for the double bond that's up here. Here's sodium bicarbonate. Sodium bicarbonate, baking soda. Here, again, this is gonna have, they're showing formal charge here, but this is gonna have 1 more resonance form. The oxygen. Here, they really aren't showing the geometry of it. They're just showing the Lewis structures. You don't have to. I mean, you can make this bond angle 180. They made it 180. Doesn't matter. This is bicarbonate. This is the resonance hybrid of bicarbonate where they smear out the double bond over 3 bond positions. Bicarbonate. I mean, not bicarbonate, incarbonate, which is different. All right, so since I didn't record that, gosh, let me just do that really quick here. Well, it doesn't. Just want to emphasize, this is tetrahedral EPG. In the plane, out of the plane, coming out, wedge, going into the plane. Here, you could leave it as formal charges. So if I wrote it like this, I wouldn't need square brackets. It's all right. The square brackets are just being, I leave the hydrogen in the same position. 1 lone pair wedges out, the other lone pair gets socked in. So it's kind of like this. This would be tetrahedral also. This is tetrahedral as well. And then this. So you could write it like this without the square brackets. If you want to be complete, this would be 100%. You know, I wouldn't deduct. This is very common that people write it like this. But if you want to be complete, then you'll sum up all the formal charges and write the net charge on the outside like that. And then the hybrid, you know, structure. We're just going to dot the double bonding electrons and smear those out over two bonds like this. Just dot it. That leaves two lone pairs fixed and then a third lone pair that's kind of floating. So the third lone pair I'm just trying to draw as dotted like this rather than two dots like this, just smeared out. The electron cloud's kind of smeared out. So that makes this -1/2 average. Charge here is -1/2 average. The net charge here is -1/2 and -1/2 is -1. And this is a 1.5 bond. In carbonate, you know, carbonate doesn't have this hydrogen, so we can throw a double bond on the right too if it didn't have that hydrogen. So carbonate's going to look different than bicarbonate. All right. All right, so I'm going to put this upload. You could do this as group work if you want, and just upload this onto Piazza. Make sure you include the geometries here: trigonal planar 120, and this was a tetrahedral. EPG, MG was bent. Angle was about 105 distorted, but 109.5 ideal. All right, Lewis structures like this are really important. But let's take a look at the next chapters. We got to keep moving here. So we'll leave Lewis structures for right now, and we're going to look at Chapter 14 is gases revisited. So let's take a look. Open chapter 14. Find that. Okay, so chapter 14, gases part 2. Here's a balloon. I think they're trying to make some record for this, but it's a combination of helium and hot air. The necessary lift. Air consists mostly of nitrogen and oxygen. There's a little bit of argon, CO2, water, etc. The amount of argon in there is very small, so we'll just say it's mostly nitrogen and oxygen. So that's what we'll pump in here. When you pump it in, you're compressing it. And so you're taking a larger volume and compressing it into a smaller volume here. So the pressure is going to go up. In airplane tires like this, they don't use air. They only use nitrogen here. And so they don't use oxygen because oxygen, of course, is an oxidizer, and the airplane is made up of things like aluminum and magnesium, which are easy to oxidize, easy to burn metals. And so they don't want oxygen around there. I think that's a reason. There's another reason people don't use air. You know, there are some places that only use nitrogen because air can have water vapor in there. And if there's water vapor in there, then water vapor doesn't behave, when we say so, ideally, you know. And so its temperature fluctuates. I mean, the pressure fluctuates more with temperature. And so a lot of people want either dry air in their tires or dry nitrogen, or just, you know, these are just nitrogen. We'll give them more consistent pressure here. Obviously, you take a bigger volume and compress it into a smaller volume, you're going to get more collisions. Also, the density is going to go up, but you're going to get more collisions, which results in more pressure. More pressure being collisions. It's there. So we're going to be looking at gas mixtures quite a lot. And so here's a mixture of oxygen and hydrogen. So we take some oxygen here, 50 milliliters of oxygen and 100 milliliters of hydrogen. One thing to note is that the volume, this is Avogadro, by the way, and this is Gay-Lussac. And so Gay-Lussac was talking about volumes. Avogadro put it into perspective of molecules. Gay-Lussac, and there's a Gay-Lussac's law, is you need 50 milliliters of oxygen plus 100 milliliters of H2. You need to react them in that ratio. Then Avogadro said, well, 50 milliliters of oxygen might have this many molecules, and 100 milliliters of H2 is going to have twice as many molecules because it has twice the volume. And so Avogadro says that the number of particles in there, the number of moles of particles, or the number of molecules is proportional to the volume. And so this is Avogadro's law. Avogadro's law says this: if I have 1 part of oxygen, I need 2 parts of hydrogen. 2 parts of hydrogen will be twice the volume. So if I have 50 milliliters of oxygen, I'll need 100 or twice the volume of hydrogen to react. And so this means, like say, for example, if I had a liter of oxygen gas, I'll need 2 liters of hydrogen gas to properly react it stoichiometrically. And the funny thing is, how many liters of gas will I form? Well, I'll form 2 liters of water gas, or water vapor. And so if 50 milliliters is 4 molecules and 100 milliliters is 8 molecules, like this, then 100 milliliters of water will have 8 water molecules. And the stoichiometry is like this: an O2 plus 2 H2s yields 2 H2Os. And so that would be Avogadro's. So this is some more Avogadro's law. Basically, H2 and Cl2 react in a 1-to-1 ratio. So if I had 1 liter of H2, I'll need 1 liter of Cl2. That's going to have the same number of molecules. So if I use 2 liters of Cl2, it'd have twice as many molecules, and I don't need it. I need it in a 1-to-1 mole ratio. 1 H2 reacts with 1 Cl2. This is going to produce 2 HCl's. Well, 2 HCl's is going to take up twice the volume, you know, than this and this. Okay, here I have excess H2. So if I have excess H2, the volume is going to be bigger. And so, this graphic isn't totally clear, but we can see it here. So if I take 8, this is 8 molecules of H2 here, and 4 molecules of O2. So let's see what happens here.
Quantity and volume are directly related. If we take 8 molecules of H2 and combine them with 4 molecules of O2, we get 12 molecules and a combined volume. If we then react the mixture, we end up with 8 molecules of gaseous H2O, which occupies the same volume as 8 molecules of any other gas.
Yeah, so 8 molecules is going to occupy twice the volume of 4 molecules. 12 molecules will have 3 times the volume of 4 molecules. So the volume is directly proportional. So here I have 3 molecules, or 3 particles. Here I have 6. So 6 particles is going to be twice the volume. And here I'm going to have 9 particles. 9 particles will be 3 times the volume of 3 particles here. So that's
quantity and volume.
Avogadro's. So here, this is this means there are different ways of thinking about gas mixtures. Here. So the mole percentage is always fixed. Mole percentage, we call mole percentage or mole fraction, is always fixed. So let me write that here. Mole fraction or percentage is always Always true. It's true. So in this case, let me see how many particles we have. If we include the argon, we shouldn't include the argon because this is way more argon than normal air has. But let's ignore. Well, maybe we'll keep it in there. So how many particles are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 particles. Actually, let's get rid of the argon. Argon is much lower quantities than this. So if I had 11 particles, it's likely I won't have an argon there. I'd probably have to have 1,000 particles in order to see 1 particle of argon. And so they're just trying to be more realistic that there might be argon there, but I'd probably need 1,000 molecules in order to see 1 argon. And so instead, we're going to say that we have 10 particles. So let's ignore the argon. And so the mole fraction is going to be this. 8 out of the 10 are nitrogen. And so what is that? That's 80% nitrogen. So 8 parts out of 10. So you just times it by 100%. That gives you 80% nitrogen. 2 out of the 10 particles is oxygen. So that's 20% oxygen. And so 20%. That's always the case here. Now, there are 2 ways of visualizing this mixture. Actually, 3 ways. This is one way of visualizing this mixture. The second way of visualizing this mixture is by Avogadro's. If we consider this as an Avogadro's mixture, then let's say this is, let's say, let's slice this up into 10 slices. Let's see, how can I slice this up into 10 slices? So 5 slices on the side. So if I slice this up into 10 slices, 1, 2, 3, 1, 2, 3. Those slices aren't so even. So, actually, it might be easier to do this. Let me just do it like this. So I'm going to have let's have 1.00 liters of air at 1.00 atmospheres. And so if I have 1 liter of air at 1.00 atmospheres, then it's true. 80% of the molecules in there are going to be nitrogen. 20% of the molecules in there are going to be oxygen. And so nitrogen stuff is blue. So if I did 100, 80 of these will be blue. 20 of them will be red. Like that. So what Avogadro says is that if I have 1 liter of air at 1 atmosphere, what does 1 liter of air at 1 atmosphere consist of? Well, 1 liter of air at 1 atmosphere consists of this. It's going to consist of 0.8 liters of nitrogen. 0.8 liters of nitrogen at 1 atmosphere. And so I'm going to have nitrogen. So I just put the nitrogen in a separate box like this. And have the nitrogen here. I'm going to have the same number of collisions. It's just a smaller box, so the pressure is going to be the same. Collisions per unit area. It's just a small box. Plus, oops. I'm going to have a smaller box that's going to be 0.20 liters of oxygen. at 1 atmosphere. And so the oxygen pressure is going to be exactly the same. It's just a much smaller box, so the collisions get the same number of collisions per unit area. That's it. And so this is Avogadro. So if I have 1 liter of air, I have 0.8 liters of nitrogen plus 0.2 liters of oxygen. And that gives me my air, 80% nitrogen, 20% oxygen by volume. And so this is what we call volume fraction. In this case, the volume fraction would be 80 out of 100, or 8 out of 10 nitrogen parts by volume, and 20 out of 100. Oxygen. That would be it. All right, so what we'll have here is it's 20% oxygen, 80% nitrogen. And so we'll just write it here. Actually, I'll just do it like this. 8 out of 10 parts will be nitrogen. And so 8 moles out of 10 moles. 8 moles of nitrogen out of 10 moles of air. Some fraction. Or it's the same 80 moles of nitrogen out of 100 moles of air. So for every 100 moles of air, I'm going to have 80 moles of nitrogen. That's a mole fraction. It's 80% nitrogen. Well, this is the same thing with the volume. I'll have 80 liters of nitrogen for every 100 liters of air. That would be it. And so the mole fraction is equal to the volume fraction. The third way of looking at this is via Avogadro's, not Avogadro's, Dalton's. Just said Avogadro's here, but Dalton's. If we look at Dalton's, then we have a situation like this. How much nitrogen do we have in this? Well, it's the exact same mixture, but in this case, I'm going to say I have 1.00 liters of nitrogen gas. Well, if I have 1.00 liters of nitrogen, then I'm going to have fewer collisions because there's no oxygen in there. The red oxygens are also colliding with the wall, but now I'm removing the red oxygen. So the only thing that's colliding with the wall will be the blue. And so if I'm missing the red collisions, I'm not going to get the same pressure. And so the pressure is going to be a little different here. And so the pressure here is going to be at 0.80 atmospheres. And so I have 1 liter of nitrogen at 0.80 atmospheres, plus, okay, I'm going to have 1 liter of oxygen, so 1.00 liters of oxygen at 0.20 atmospheres. And so it's going to be the same size box, except now, all those oxygens are responsible for the pressure, and there just aren't that many, so the pressure is going to go down quite a lot. And so we give 2 names for this. Avogadro's is called constant pressure. The pressure doesn't change. So the pressure of the air is 1 atmosphere. The pressure of the nitrogen is 1 atmosphere, and the pressure of oxygen is 1 atmosphere. It's constant pressure. What changes is the volumes. The volumes add up. So 0.8 liters plus 0.2 liters equals 1.00 liters. The volumes add up. The pressures are the same. So 1 atmosphere is equal to 1 atmosphere, which is equal to 1 atmosphere. It's constant pressure. Under Dalton's, we have something called constant volume. Constant volume. So the volume doesn't change. That is 1 liter plus 1 liter equals 1 liter. In other words, 1 liter is the same as 1 liter, which is the same as 1 liter. Just like over here, 1 atmosphere plus 1 atmosphere is equal to 1 atmosphere. But here, 0.8 atmospheres plus 0.2 atmospheres gives us 1.00 atmospheres. And so the pressures add up. These are called pressure fractions here. And so we can add that into this equation up above here. And so if I add this to the equation here, then that means I'm going to have 0.80 atmospheres of nitrogen for every 1.00 atmospheres of air here. And so the mole fraction is equal to the volume fraction, which is equal to the pressure fraction. But there are restrictions. The mole fraction is always true, regardless. The volume fraction is only true if we're working under constant pressure. And so the volumes add up here. 0.8 liters plus 0.2 liters gives us 1 liter of air. The volumes add up if we're at constant pressure and temperature. The pressure fractions, the pressure fraction will add up as well, or will be the same as long as we're under constant volume conditions. So true if constant volume. And so there are different ways of visualizing it. When we're doing chemical reactions, it's nice to visualize it like this, you know, as volume fractions. And so when we're doing chemical reactions, we like to use Avogadros in doing chemical reactions and stoichiometry. When we're doing other things, sometimes it's easier to use Daltons. And which way we do it, whether we look at a mixture as being Avogadros or Daltons, depends on the problem. These drawings. So here I like to do it using Avogadros. You know, 1 liter of hydrogen needs 1 liter of chlorine, which is going to make 2 liters product in this case. We'll look at that again later and when we're doing some more mixtures. For right now, what we're going to do is we're going to combine Boyle's, Charles, and Avogadro's. Avogadro's law is just the volumes directly proportional to the number of moles, number of particles. And this is fixed pressure, that is constant pressure. Now, ideal gas law is combining these 3 into 1. So we get PV equals nRT. It's our ideal gas law. Or PV over NT is equal to R, which is a constant. So this is where R is equal to 0.0. I only have it memorized for atmospheres. So 0.08206 liters times atmosphere per mole times Kelvin. So I just make sure, you know, I make sure the volumes are in liters. I make sure the pressure is in atmospheres. And I make sure the temperature is in Kelvin when I use this equation here. R is the ideal gas law constant. This one just comes from the equation. And so what types of problems can we do? Well, the types of problems we can do is given 3, determine the 4th. And so in order to characterize a gas, we look at the pressure, we look at the volume, and we look at the temperature and the amount, the number of moles. So if we're given 3, we can figure out the 4th. So given 3, determine the 4th variable. And so that's a standard ideal gas law calculation. So what is the temperature when the pressure and volume equals that? And so let's look at the next slide here. So let's do one. calculation here. What is the volume? This volume's special. That box contains 22.4 liters of gas, I think. Well, this volume's special. I know this volume because I had to memorize that volume when I was a Chem 4 student. I had to memorize that. I still have it memorized. This has to qualify as the most useless thing I've memorized in chemistry. It's useless because I just never used it. So why bother memorizing that? Problem is I can't forget it. I've seen this so many times, it's impossible for me to forget this number. Which is too bad because I have a limited amount of memory and I don't want to waste it thinking about that number. But where did that number come from? So that number came from this. What is the volume when the pressure is equal to 1 atmosphere? Let's say exactly 1 atmosphere. The temperature is equal to exactly 0 degrees C. And the number of moles is equal to 1 mole of gas. So if I had 1 mole of gas at 1 atmosphere and 0 degrees C, what volume would that occupy? And so the volume is going to equal, we rearranged the ideal gas law, it's going to be nRT over P. So we'll plug in 1 mole here. Let's say we have exactly 1 mole. And then R is 0.08206 liters times atmosphere per mole Kelvin. And then T, well, that's going to be 273 Kelvin. So that's 273 Kelvin divided by P, which is 1 atmosphere. And so the moles cancel, the atmospheres cancel, the Kelvins cancel, and that leaves us with liters. And this comes out to 22.4. Actually, the more sig figs. I only memorized it to 3 sig figs. But we're allowed 4 sig figs in this calculation. So let me calculate it to 4 sig figs, 0.08206 times 298, 24.45. 24.4, I don't know why I memorized it at 24.4 liters, 24.453 liters. This is something called the molar volume of a gas, because it's the volume of 1 mole of gas. The molar volume of the gas we could write like this, 22.453 liters of gas for every 1 mole of gas at 1 atmosphere and 273 Kelvin. The reason why this number wasn't so useful is because of this temperature. This temperature is not a very common temperature that you would set the AC to inside the laboratory. If you worked in a freezer, then it would be fine, but most people don't work inside a freezer, and therefore it's not a very useful number. Okay, I missed it. What does it say about volume fraction? Constant pressure. 80 out of 100. 80, it was a volume fraction. It would be 80 liters of hydrogen or nitrogen for every 100 liters of air. This would be a constant pressure. Said. And so I had to memorize this molar volume, but it wasn't very useful because the temperature is not a common temperature. Let's determine the molar volume of something that's a little more useful. Maybe. And so that was an example of calculating a single variable. Now we're going to look at molar volume. Molar volume has a formula like this, V over N, V per N. is liters per mole. And then V over N is equal to RT over P, which is the molar volume. V over N is the molar volume. So the molar volume we can calculate at any temperature and pressure. Molar volume is easy to calculate. At any T and P, at any temperature and pressure. Because all we need is the temperature and pressure. We know what R is already. And so let's pick one. Determine the molar volume at 1 atmosphere. 1 atmosphere is very common pressure. So you're just your normal atmospheric pressure, which is close to 1 bar. And room temperature, it's supposed to be and 298 Kelvin. 298 Kelvin is pretty much room temperature. And so let's determine the molar volume there. The molar volume is the volume per mole, liters per mole. And that's going to equal R, 0.08206 liters times atmosphere per mole times Kelvin, times T, which is 298 Kelvin, divided by P, which is 1 atmosphere. So the atmospheres cancel, the Kelvins cancel, and that gives us liters per mole, so units. So let's see what this comes out to here, 0.08206. Times 298, 24.45 liters per mole, which is 24.5. If I'm going to memorize it to 3 sig figs, I'd do this, or to 4 sig figs, I'd do this. Yeah. So about 24.5 liters per mole. And so if this were 24.5 liters, which it is, this is close to 24.5 liters, it looks like it. But if it were, that would be a mole of gas right there. That would be an Avogadro's numbers worth of molecules. If this aired, it'd be cumulative Avogadro's numbers worth of nitrogen and oxygen, and then some argon and CO2 and water. Okay. B, determine molar volume at 1 bar and 298 Kelvin. So rather than doing it at 1 atmosphere, let's do it at 1 bar. And so V over N is equal to 0.08206 liters times atmosphere per mole Kelvin. Now I need to change the bar into atmospheres. And so I have, let's say it's exactly 1 bar. And the conversion factor for converting bar into atmospheres is 1 atmosphere. This one you don't have to memorize, is equal to 1.01325 bar. And so the bar cancels. Oops, it's wrong. RT over P should be divided by. So the bar cancels, it leaves us with atmospheres here. And so this is RT. T is 298 Kelvin. So Kelvin cancels. Atmospheres cancel. Leaves us with liters per mole. And so if this were at 1 bar, what would the volume be? And so 0.08206 times 298 times 1.01325, 2477. So this would be 24.77 liters per mole, or about 24.8 liters per mole. So roughly, there's about 25, we'll just say roughly. Roughly 25 liters per mole gas under approximately normal conditions. So that's molar volume. Let me do something really quick.
He just said.
Okay. So molar volume is the common calculation that we do. We often do molar volumes at different temperatures and pressures, but it's easy to calculate because this is the equation for it. This equation is just, how I got this equation is just rearranging the ideal gas law. Let me just add that. This is easy to derive because PV is the nRT. So we divide both sides by P and N. So we'll get V over N is equal to RT over P. So that's going to give us this equation here. This next equation is what we call the gas density. This is CO2. CO2 gas is more dense than air, so it sinks. Helium is lighter than air, so it floats. CO2 is heavier than air, so it sinks. And that's all related to the density. And so let's look at the density. Density of gas. Density of a gas is the mass over the volume. But we know from the ideal gas law, volume is equal to nRT divided by P. So we'll just solve for V here, the ideal gas law, and this is the equation we get. And so the density is equal to the mass divided by nRT over P, which is equal to the mass times pressure divided by nRT. Now, the interesting thing about this equation is this: mass over N is the molar mass. That is grams per mole. And so what we could do is we could rearrange the equation yet again here. And that is, this is equal to the molar mass. So I'll write mm for the molar mass. Molar mass times P divided by RT. So I can determine the density of a gas just based on its molar mass and the pressure and temperature that I want. So let's figure out the density of CO2 gas. The density of CO2 gas is equal to the molar mass of CO2 gas. The molar mass is 44.01 grams per mole. This is for CO2. Times the pressure, let's go with 1 atmosphere of pressure, divided by R. So we'll just go 0.08206 liters times atmosphere per mole Kelvin. And then the temperature, let's go with 298 Kelvin. Here. And so looking at the units, the atmospheres cancel, the Kelvins cancel, the moles cancel, and that gives us grams per liter. And so let's see what the density is in grams per liter. That's 44.01 divided by 0.08206 divided by 298, 1.79. So in a liter of CO2 gas, we have about 1.799 grams worth of CO2, or it's going to weigh about 1.8 grams per liter. How about air? Air is about 1.2 grams per liter. The average molar mass of air is around 29. So this is more than half this. So the CO2 should sink now. All right, this is gas stoichiometry. In gas stoichiometry, well, we already had energy, we already had grams. Here it is. It's the gas volume. If we have the gas volume, we can figure out the moles. You know, there are two ways to do that. And so here, to go from volume of gas to moles of gas, the moles of gas is just equal to PV over RT. You know, we could calculate it. Or that's option 1. Or option 2. Option 2 is use the molar volume as a conversion factor. Use molar volume as a conversion factor. So, yeah. And then we can do some gas stoichiometry. The other thing we could do is we could do direct liters to liters. That is, we can skip this mole to mole transition and go to liter transition. This is a liter to liter conversion, as long as the you know, as long as Avogadro's law holds, as long as we're at constant pressure, we're okay. And so here, if I need 1 liter of hydrogen for every 1 liter of chlorine, vice versa. So there's a reaction of 1 liter to 1 liter. So what we can do is we can use the mole fraction. Mole fraction is 1 mole of hydrogen plus 1 mole of chlorine is going to yield 2 moles of HCl. And so the mole fraction is 1 to 1 to 2. So 1 to 1 to 2 mole fraction, you know, kind of thing. It's the same as the volume fraction. So if I have 1 liter of hydrogen, I'll need 1 liter of chlorine to produce 2 liters of HCl. All these have to be gases for this to work. And so the mole ratio is the same as the volume ratio, which is the same as a pressure ratio. And so 1 liter, 1 liter, 2 liters is the same as the pressure ratio. 1 atmosphere, 1 atmosphere, 2 atmospheres. As long as, well, if we're dealing with volume, as long as we're under constant pressure, and if we're dealing with pressure, as long as we're at constant volume. Okay. And so we could do a direct mole-to-mole conversion or here, but we can also do a direct liter-to-liter conversion out here. That speeds things up. All right, I think it's break time now. So let's go ahead and we're going to take a break here and pause the recording. Hopefully I don't forget to start the recording again. Otherwise there'll be another gap. Okay, so let me pause. Okay, we're going to resume here. So let's take a look at some problems from chapter 14. Compare the volume of 1 times 10 to the 23rd hydrogen molecules to 1 times 10 to the 23rd oxygen molecules and 2 times 10 to the 23rd nitrogen, all at the same temperature and pressure. And so 1 times 10 to the 23rd and 1 time, these have the same number of molecules. So hydrogen and oxygen are going to have the same volume, whereas nitrogen's twice the number of molecules, so that'll have twice the volume. And so So nitrogen is going to have double the volume. That's basically what this is saying. Let's take a look at just these ones. Find the pressure and torr produced by 0.088 moles of carbon dioxide in a 5-liter vessel at 36 degrees C. So this is a PV equals nRT problem. Actually, let's see, for this problem, we have the pressure, which is the unknown here, it's P. We have the moles here, we have the volume here, we have the temperature here. So we have everything except R. R we know. So we're going to solve for the pressure. Pressure is equal to nRT over V. So let's go ahead and plug in the moles, 0.0888 moles. It doesn't matter what the gas is. This gas is CO2, but it doesn't ask us what the gas is here. Times R, 0.08206 liters times atmosphere per mole Kelvin. You should memorize R to 4 sig figs, 0.08206. That's the gas constant. This comes from PV equals over NT is equal to a constant. When you solve this equation or plot it, the constant comes out to 0.08206 liters atmosphere per mole Kelvin, and that's what we call R. Temperature, this temperature needs to be converted into Kelvin. So 36 plus 273 is going to give us 309 Kelvin divided by the volume 5.0 liters. Now this is going to give it to us in atmospheres. And so if we get it in atmospheres, and then we can just, we can do it here too. If we want in torr, we can just add one more, 760 torr per atmospheres. So we can take the answer that we get from here and just convert it into torr by multiplying by 760 torr per atmosphere. Let's see what they did here. So PV equals nRT over V. Now they used a different R. I don't like to memorize too many different R's. This is the R value when we're using torr. I only like to memorize one R value, or actually two. This one, and there's one other, the thermodynamic R value that's useful to memorize. I don't like to memorize a whole bunch of others. And so your book has these, but I don't use it. If I take this one and multiply by 760, then I'll get theirs, which I don't want to do. And convert it into Kelvin. So I just added one more conversion factor. I know this conversion factor, I know R. And so the fewer things I have to memorize, the better. So I don't even bother ever using this. I never use this and I never memorize it, because I don't want to memorize to 4 sig figs. This is only 3 sig figs. Anyway. So let's see how I'm gonna, since they're doing differently, let me try mine here. Mine's gonna be 0.0888 times 0.08206 times 309 times 760 divided by 5, 342. I get 342.2 torr. Well, pretty much the same answer. 342.2 torr. Or 342 torr. All right, so it's a standard ideal gas law calculation. It's just algebra, plug in the variables kind of thing. The pressure exerted by 6.04 moles of nitrogen monoxide. You know, nitrogen monoxide is also called nitric oxide. So that's N. Temperature is T. This is P. What's the volume? So the volume is equal to nRT over P. So let's just plug it in, 6.04 moles. Temperature we have to convert into kelvins. Atmosphere we just leave. So and then R is our standard R. Let's see what they use for R. Here. All right, they used R to 3 sig figs, which is 0.0821, which is okay for Chem 4, but for Chem 1A, you'll need it to 4 sig figs. So you might as well just start memorizing it to 4 sig figs. It'll be easier that way. And so this one I wouldn't have used. I would have used 0.08206 liters atmosphere per mole Kelvin. Moles, convert that to Kelvin, and then just plug in everything, 8.39 liters. I want to see the rounding step though. It should be 8.3 something something, and then rounded to 8.39. So. A 784 milliliter hydrogen lecture bottle is left with the valve slightly open. Assuming no air has mixed with the hydrogen, how many moles of hydrogen are left in the bottle after the pressure has become equal to an atmospheric pressure of 752 torr at a temperature of 22 degrees C? So pretty soon this bottle becomes empty, basically, but it's not totally empty. There's still a little bit of residual hydrogen left in there, so the valve is open. What's going to happen is air can diffuse in, but they say you caught it before the air starts to leak in, and the hydrogen leaks out, and you get a mixture of air and hydrogen in there. And so, in other words, it's kind of empty, but it's not empty. There's still hydrogen left in there. And so how much hydrogen is left in there? And so we have the pressure, we have the volume, we have the temperature. And so we want to know how many moles, N. So we solve for N. N is equal to PV over RT. So we're going to have to convert the pressure into atmospheres. That's not a big deal. You know, 752 torr converted to atmospheres is 1 atmosphere is 760 torr. So the torr cancel. And then V, we want to convert from milliliters to liters. We could probably do that in our heads. That's 0.784 liters. Just move the decimal 3 over. And then R, we use the same R, 8206 liters times atmosphere per mole Kelvin. And then the temperature, 273, that would be 295 Kelvin. Comfortable temperature. And so plug those in. Let's see what we get. Let's see what the book did. Okay, again, the book used this R with torr. I just convert the torr into atmospheres and then just use the same R over and over and over again. So that's what they'll get here. The moles, they converted milliliters to liters like we did, and they converted Celsius to Kelvin, we did. At what temperature, degrees C, will 0.810 moles of chlorine in a 15.7 liter vessel exert a pressure of 756 torr? So this one's going to be an additional algebraic step to it because the temperature we're going to get is going to be in Kelvin. And so here we have moles, here we have volume, here we have pressure. So we're going to have to convert the pressure from torr to atmospheres. And we're going to have to convert the temperature from Kelvin to Celsius. And so the temperature is equal to pressure volume over RT. And so the pressure, we'll convert it to atmospheres, 756 torr. 1 atmosphere is equivalent to 760 torr. And then the volume is good, it's 15.7 liters, that's what we want. Divided by R, the same R, always 0.08206 liters times atmosphere per mole Kelvin. Even when I'm working in bar, I don't use the bar one. Your book will use the bar one. I don't bother memorizing that one. I just convert atmospheres to bars, which, and then the temperature. I mean, actually we're solving for temperature, so NR and the number of moles. And so 0.810 moles. So let's see what they did. Okay, again, they're going to use this 62.4. I don't use that. Essentially, it's the same thing. So solving for one unknown. Okay, once they get the Kelvin temperature, then they have to convert the Kelvin temperature into Celsius by subtracting 273. And so you get minus 38 degrees C. And so this is the additional step. So step 1, ideal gas law. Step 2 is convert Kelvin into Celsius here. How many moles of carbon monoxide? So we're looking for moles, N. Must be placed in a 40, so this is the volume. This is the pressure. Again, pressure needs to be converted to atmosphere and temperature needs to be converted into Kelvin. Let's solve for moles. Let's solve for moles. N is equal to PV over RT. Pressure, volume, R, T, 2.13 moles. Find the volume of 0.621 moles of helium. So, all right, so we were looking for the volume. We're given the moles, we're given the temperature converted to Kelvin, and we're given the pressure. The pressure we don't need to convert. The pressure is already atmosphere. So this is going to be our standard R. Except our standard R is 4 sig figs. The book's R is 3 sig figs. So I wouldn't use this one here. I'd use the 4 sig figs. It's 15.9. Solving for the volume. Okay, let's take a look at the next calculations here. The STP. Now, STP is standard temperature and pressure. STP is not so useful, as I said before, because of the standard temperature. Standard temperature is 0 degrees Celsius. And the problem with 0 degrees Celsius is nobody works at 0 degrees Celsius, at least not comfortably. And so the temperature is equal to 0 degrees C. The pressure is equal to 1 bar or 1 atmosphere. Your book is going to pick 1 bar. Other books will pick 1 atmosphere. They're close. The STP density of an unknown gas is found to be 2.32 grams per liter. And so here we have to use that density equation. Density is mass over volume. But volume is equal to nRT over P. So what we're going to do is we're going to substitute this in, and then we'll get the density of the gas is equal to mass times pressure divided by nRT. But mass over N is molar mass. So this is equal to the molar mass times the pressure over RT. So what is the molar mass of the gas? So we solve for the molar mass of the gas here. So if we solve for the molar mass of the molar mass of the gas is equal to the density of the gas times RT divided by P. That's one way we could do it. There's another way of doing this too. The other way of doing this is to solve it from the molar mass. Or we could have solved it like this. The molar mass of a gas is equal to the mass of the gas divided by N. But we know that N is equal to PV over RT. And so we substitute that in there. So substitute this for N, and that means the molar mass of a gas is equal to the mass divided by PV over RT. And what that's going to equal is going to equal the mass times RT over PV. Mass over volume is the density. So this is equal to the density times RT over P. Well, it's the same thing we got here, density. I used it capital D. It doesn't matter, capital D or lowercase d. There's two ways of deriving this equation here. So we plug in the density here, we have that. We know what R is, we know what the temperature is, we just got it 0 degrees, we got to convert it to Kelvin. That's 273 Kelvin, plug that in here. The pressure we're going to use is 1 bar. If we use the pressure 1 bar, then we have to do one more conversion factor here because I have the R memorized for atmospheres. And so let's plug in the density here, which is 2.32 grams per liter times R, 0.08206 liters times atmosphere per mole Kelvin times the pressure. The pressure is going to be 1 bar. Our book uses 1 bar. Now I have to convert that. And so 1 atmosphere is equivalent to 1.01325 bar. And so I'll just do a bar to atmosphere conversion here, divided by the pressure. Oops, that was the pressure. Divided by the pressure, and the temperature should be up here, 273 Kelvin. The units should cancel out. Got to make sure the units cancel out. So what does that give us? As far as units go, let's make sure the units do cancel out. And so let's take a look here. Liters, cancel out liters here. Okay. Kelvin cancels out Kelvin here, grams per mole. Atmospheres cancel out atmospheres, and bars cancel out bars, leaving me grams per mole. Well, molar mass should be grams per mole. And so let's figure out what I got here. 2.32 times 0.08206 times 273 divided by, actually this invert multiplied, times 101, 1.01325. 52.65 grams per mole. And so let's see what they got here. 52.65 grams per mole is round to 52.7 grams per mole. So that's what they got. They use bar, yeah, they use bar, but you see they use the R in atmospheres and then converted the pressure into bar. They didn't use all the sig figs, 101.325. They just used 101.3. 101, I remember 101.325 because it's exact. They're exactly 101.325 bar in an atmosphere. That's the only reason I memorized it out to 6 sig figs. The effective molar mass of air is 29 grams per mole. You know, the molar mass of oxygen is 32 grams per mole. The molar mass of nitrogen is 28 grams per mole. And since air is mostly nitrogen, the molar mass is closer to nitrogen. And so it's around 29, it's 80%. You know. And so that's what we have here. So use this value to calculate the density of air at STP. So the density of air, we just need the equation. There are different things you could do. You can memorize the equation, or you can just derive it, figure out how to derive it. You know, if we memorize the equation, the density is equal to the molar mass times P over RT. I think that was it. Well, we could check the units. The way you can check if the equation's correct or not, let's say you memorized it, but you just can't remember if this is exactly right or not. This is grams per mole. We do it by units. This is going to be atmospheres. Okay, and then down here we have liters times atmospheres per mole times Kelvin. Temperature is going to be in Kelvin. So the Kelvin cancels out the Kelvin, the atmospheres cancel out the atmospheres. The moles cancel out the moles, and this gives us grams per liter. So the dimensions work out. So this is the correct equation because the units will work out. And so we just got to plug in the molar mass. And standard temperature is 273 Kelvin. Standard pressure is 1 bar. And so we're going to have to convert bar into atmospheres if we're going to use our standard R here. Let's see, I think that's what they do. Yeah. See, they're going to convert, this is 1 bar standard, and so they convert bar into atmospheres. Okay. The density of air is 1.3. It's like 1.28 or something like that, rounded to 1.3. If this is 2 sig figs, it's 2 sig figs in the molar mass here. So that's what we got. Now, if we change the temperature, let's say it's warmer, the pressure is a little less, what is the density? You know, so we'll just plug in the different temperature and different pressure here. Now we're at torr. So if we're at torr, I'd convert this to atmosphere and then convert it into bar. Or actually, I wouldn't convert it into bar. I'm already using this in atmospheres. I just convert it into atmospheres. They didn't just yet. You can see the density went down at higher temperatures, a little less dense, you know, but it's a little lower pressure. So temperature is going to decrease, but the pressure decrease will change it a little bit. Let me just do one thing really quick. Okay, if the density of an unknown gas is at 41 degrees C, oh, let me do one thing. What is its molar mass? And so we need the other equation. So either we memorize it or we derive it. And so if we try to memorize it, let me see. Molar mass, let me see if I remember it, is equal to the density times, well, density is in grams per liter. And the molar mass is in grams per mole. So we need the liters to cancel out. And so it's got to be density times volume, and liters will cancel out. And then we need grams per mole. And so we need RT. I think that's it. So we could use dimensional analysis if we don't want to derive it. We can just play guess and check, guess and check. A guess and check would be like this: grams per liter, volume is in liters, so liters cancel. R is in liter, oops. R is in, what is R in? Liters, atmosphere per mole Kelvin. Temperature is in Kelvin. Something's not quite right. So liters cancel, but this liter, I still have this liter here, so I screwed this up. This equation. The units don't quite work out here. And so there are 2 ways to derive the molar mass. One way to derive the molar mass of a gas is just, we know that the molar mass of the gas is mass, grams over moles, N. And then we'll substitute N. N is equal to, using the ideal gas law, is equal to PV over RT. And we'll substitute that in here. So this is mass divided by PV over RT. And what we'll do is we'll invert and multiply. So the molar mass is equal to mass times RT divided by PV. Now mass over volume is the density. And so that's density times R times T over P. So I was off. And so we know what the density is. We know what the temperature is, and we know what the pressure is. And so we just convert the temperature into Kelvin. And should be all right. And so we have this. Molar mass is equal to mass over volume is the density. Mass over volume is the density. So density times R times T over P. So here's the density times R times T over P. So 15.9 grams per mole would be the molar mass of the gas. The gas in an 8.07 liter cylinder at 13 degrees C has a mass of 33.5 grams and exerts a pressure of 3.25 atmospheres. Find the molar mass. They don't give us the density, but they give us the grams per mass per volume. So we can use that as the density. Do one thing really quick. I'll be right back. Okay, here we have mass over volume. So we're going to use that as the density here. Mass over volume. I just took the mass and volume and just called that D for density. But here we'll just plug in the mass, 33.5 grams over the volume 8.07. If we divide those two, that would be the density. And we can get the molar mass here. NO2 and N2O4 both have the same empirical simplest formula. At a temperature and pressure which both substances are gases, can you tell without calculating which gas is more dense? Well, these will have the same, if the volume of the balloon is the same, they'll have the same number of molecules. And so this has the same number of molecules as this, but the molecules weigh different amounts. This molecule is twice as heavy than this. This molecule is twice as heavy, but because of Avogadro's law, we have the same number, and these are twice as heavy, so this will be twice as dense. And so N2O4 is the red balloon, NO2 is the blue balloon. So N2O4 is more dense, it's a red balloon. Compare the molar volumes of helium and neon at 30 degrees C. The molar volume is going to be exactly the same because the molar volume does not depend on what the gas is. So helium and neon are going to have the exact same, just like the molar volume of any gas is the same. 1 mole of gas occupies about 25 liters. That means 6.022 times 10 to the 23rd particles of gas occupies about 25 liters, and it doesn't matter what the gas is. And so the molar volume is independent of the identity of the gas. So we can calculate the molar volume. The molar volume is the volume per mole. Solving the ideal gas law, it's RT over P. I use, the other R here, but, I don't know what they're doing torr. I would have converted this into atmosphere and used the other R. And so it comes out to 1.72, 1,720 liters per mole. That must be, Tom, why is it so big? Oh, because the pressure. This is like a vacuum. And so the temperature is like normal temperature, 30 degrees C, but, well, it's hot. 30 degrees C is hot. But the pressure is incredibly low. That's why the volume is so huge. Normally a liter of gas occupies 25. A mole of gas occupies 25 liters, but in this case, a mole of gas occupies 1,720 liters. It's because of the vacuum. It's 1.1 torr, very low vacuum, very low pressure. Find the molar volume of acetylene. Okay, so all we need is, it's RT over P. So we need R, which we have, T, convert that into Kelvin, and P, leave it in atmospheres. So RT over P, molar volume is RT over P. So this is a little colder, so the volume's a little smaller, but the pressure is a lot lower. It's 9/10 of an atmosphere rather than 1 atmosphere. So lower pressure means bigger volume. So normally it's about 25 liters. And it's expanded out to about 27 liters. Here, this is incredibly low pressure, so that's why it expanded so much. One small-scale laboratory method for preparing oxygen is to heat potassium chlorate in the presence of a catalyst. And so KClO3. And so just yields 2 KCLs plus 3 O2s. Find the STP volume of oxygen that can be produced. By 5 points. This is, STP is not so realistic because we aren't going to do this at 0 degrees C. So I don't like this problem. I would have done this problem with RTP, you know. I think that would have been a lot more useful. Room temperature, standard pressure. Find the RTP volume of oxygen that can be. And so RTP, room temperature, we're going to take as 298 Kelvin or 25 degrees C or about 77 Fahrenheit. And the pressure I'm going to use is 1 atmosphere. Atmosphere here. And so this is an example of stoichiometry calculation. In the stoichiometry calculation, I would do it like this as far as setting it up goes. I have 5.74, so I'm going to go 5.74 grams of KClO3. And then I'm going to go to moles of KClO3. And then from moles of KClO3, I'm going to go to moles of O2. Now from moles of O2, I'm going to go to volume of O2. Now there are two ways I can go to volume of O2. One, I could use the ideal gas law, or two, I could use the molar volume. So one, use the ideal gas law. Volume is equal to nRT over P. Two, use the molar volume. Now I know the molar volume at RTP. The molar volume at RTP is 24.5 liters per mole. And so at RTP, V over N is 24.5. V over N is equal to 24.5 liters per mole. And so we could use that as a conversion factor. So I'm going to use method 2 here. So let's see what they did here. They use method 2 also. They went 5.74 grams to moles. Moles of KClO3 to moles of O2. It's a 3:2 mole ratio. And then they use the molar volume. They use the molar volume at STP with 1 bar. I had the molar volume at STP for 1 atmosphere memorized, 22.4. With 1 bar is slightly lower pressure, so it's slightly greater volume, 22.7. But I'm not going to have you guys memorize this. They're probably making students nowadays memorize this number. But 0 degrees C is not a common temperature. And so we'll use RTP. This is my notation, room temperature, standard pressure. And so here I'm going to change this to something more realistic. Rather than using this molar volume, I'm going to use this molar volume, 24.5 liters of O2 for every mole. This is any gas. And so it could be air, 24.5 liters of air per mole of air, or O2, or whatever gas we want. A mole of gas is going to be that much. And so it's going to be a little greater volume because I'm doing a much warmer temperature. So let me take a look here. It's going to be 5.74 divided by 122.55 times 3 divided by 2, that's the mole ratio, times 24.5, 1.72. So I'm going to 1.721 liters of O2 at room temperature in 1 atmosphere. If it's under 1 bar, then it's going to be slightly bigger, about 1% bigger volume. We're at 1 bar because 1 bar is slightly smaller pressure than normal atmospheric pressure. Hey, again, they're doing STP. Your book loves STP. Loves STP. I don't love STP. I don't because let's do it at RTP. All right, so what we need to do is we need to produce 9.81 liters of chlorine gas. So we're going to have 9.81 liters of chlorine gas. And then we have two choices. We want to go to moles. Choice one, we use the ideal gas law. Ideal gas law is number of moles is equal to PV over RT, PV over RT. Or two, we use the molar volume. Molar volume. I'm going to use the molar volume at RTP. Well, I know the molar volume at RTP. The molar volume at RTP is going to be 24.5 liters of gas per mole of gas. That's what we have here. And so I'm going to use method 2. I think the book uses method 2. Once we get moles of chlorine, then we're going to go to moles of potassium permanganate over here. And then moles of potassium permanganate to grams of potassium permanganate. So let's see what they did here. So they have liters of gas to moles using STP molar volume, okay, which is 22.7, but I'm using RTP molar volume, which is 24.5. And so mine would be here. I'll change this here to 24.5. That's pretty much under standard conditions. And once I get moles of chlorine, you know, based on how many liters, each, you know, this is less than a mole. A mole would be 24.5 liters. And then I get the mole ratio from the balanced chemical equations, 2:5 ratio. And then the molar mass of potassium permanganate, I'd have to calculate it or look it up. 27.3 grams. So if I have 27.3 grams of potassium permanganate reactants in this reaction, it should produce 9.81 liters of chlorine gas here. Okay, one source of sulfur dioxide. Let's see, what are they asking here? May be solved by the molar volume method or by the ideal gas. That's choice 1 or choice 2. I call this choice 2, molar volume. Choice 1 was the ideal gas method. In the answer section, the setups are given first for the molar volume and then for the ideal gas law. So they give us both setups here. That's nice. Let's take a look. One source of sulfur dioxide, SO2, used in making sulfuric acid comes from sulfide ores by the reaction of, this is pyrite, iron disulfide they call it. So we take pyrite and burn it. We can make rust and sulfur dioxide. How many liters of sulfur dioxide gas measured at 983 torr and 214 degrees C are produced by the reaction of 598 grams of FeS2? Now, this, I don't have this molar volume memorized. I have the molar volume at 760 torr, which is 1 atmosphere, and room temperature memorized, but this is much hotter and a little higher in pressure. But it's easy. I don't have the molar volume memorized, but I can easily calculate it. And so let's see which one they did first. Okay, this is the molar volume one. And so what they did was they went from grams of FeS2 to moles of FeS2, from moles of FeS2 to moles of SO2 here. And then from moles of SO2 gas to liters using the molar volume. So where did the 30.9 liters of SO2 per mole come from? This 30.9 came from a calculation. They would have to do the calculation beforehand. And so what was the calculation that they did beforehand? And the calculation they would have had to do is this: the molar volume, which is equal to the volume per mole, V over N, is equal to RT over P. And so calculating this, R 0.08206 liters atmosphere per mole Kelvin. T, 214 plus 273, it'd be 487 Kelvin. divided by P. Now the P is 983 torr, but I need atmosphere. So let's go 983 torr and then convert that into atmosphere. 1 atmosphere is 760 torr. Down. So the torr cancel, atmospheres cancel, Kelvin cancels, and that gives me liters per mole. So how many liters per mole is that? That's going to be 0.08206 times 482. Oh, not 482, 487 divided by 983 times 760. I'm going to invert and multiply. 30.89. So I get 30.89 liters. How many? We're allowed 3 sig figs, liters per mole. And so they just rounded it to 30.9 liters per mole. So they had to do this calculation first before using method 2. To use method 1, they didn't. To use method 1, what they're going to do here is they're going to stop here. So they'll go from grams of FeS2 to moles of FeS2, from moles of FeS2 to moles of SO2, and then stop here to do method 1, and then plug that in up here. Oh, actually, they did the calculation. Here's the calculation for molar volume. So if I do the ideal gas law, this is not method 1. This is the pre-calculation that we did. So we'll call it I. So method 1 here is we stop here and then calculate the volume. The volume is equal to nRT over P. So they'll plug in the moles of SO2 here. This is going to be the moles of SO2 that they get here. So that's going to go here. And the temperature is given, the pressure is given, and R, you should know what that is, and then do the algebraic calculation, you'll be able to get that there. And so you have a choice of methods that you could use to do it. I thought they were going to show both, but they didn't show both. Okay, we'll look at the next one here. How many grams of water must decompose by electrolysis to produce 23.9 liters of hydrogen measured at 28 degrees C and 782 torr? So if we're going to use the molar volume method, first thing we have to do is calculate the molar volume, because this I don't have memorized here. So we'll have to calculate that. Just one second, I'll be right back. Okay, I'm back. So here we're going to have to calculate the molar volume if we're going to use the molar volume method, or we could use the other method. In this case, it doesn't really matter which method you use, because in this case, you might think, okay, it'd be easier to do the ideal gas method. If we did the ideal gas method, then this is what we do here. We have the pressure, we have the volume, and we have the temperature. So we're going to calculate the number of moles. So the number of moles of hydrogen gas is equal to PV over RT. And so we could just plug in the pressure, 728 torr, and then we got to convert that to atmospheres. So 1 atmosphere is 760 torr. And then we have the volume, 23.9 liters of hydrogen divided by the R, 0.08206 liters atmosphere per mole Kelvin, and then the temperature, 273 plus 28 is going to be 301 Kelvin, 301 Kelvin. And so we can calculate the moles. And once we have the moles, then electrolysis of water, this is the equation here. 2 waters liquids can be electrolyzed to form hydrogen and oxygen gas. So once we have the moles of H2, then we can go from moles of H2 to moles of water. And then from moles of water, we can go to grams of water here. And so there are 2 ways to get the moles. You know, one way is using the ideal gas. The second way is by using the molar volume, but I didn't do the molar volume in this case, but I could have calculated it as well. Let's see which method they used. They calculated the molar volume. So the molar volume is just RT over P. And so it's 25.8 liters per mole of gas under these conditions. And then they just did this, 23.9 liters of H2 to moles. Molar volume allows us to go straight from liters to moles or moles to liters. And then from moles of hydrogen to moles of water to grams of water. So the advantage of doing molar volume is it just throws it into a dimensional analysis problem here. We just have to calculate the conversion factor here first, rather than setting up an algebraic equation here. And the problem with doing it, the ideal gas method, is people don't track which moles we're talking about. And so one of the most common mistakes is that people will think this mole is for any of these, and end up getting it wrong. So, for example, they need moles of O2, but they calculate moles of H2, but they didn't keep track of it. And so that's a disadvantage. A lot of mistakes are made. So I think there are fewer mistakes made with the molar volume method. But there shouldn't be any mistakes with either method. Either method should be fine. All right, let's take a look at the next one. The reaction chamber in a modified Haber process for making ammonia by the direct combination of its elements is operated at 575 degrees C and 248 atmospheres. How many liters of nitrogen measured at these conditions will react to produce 9.16 grams of ammonia? And so, the Haber process is going to involve nitrogen plus hydrogen yields ammonia. Since we don't like fractions in stoichiometry, let's go with 2 ammonias, and that's going to give me 3 hydrogens here. Yeah. So looking at this, we're going to go from grams of ammonia. So grams of ammonia to moles of ammonia. And from moles of ammonia, we want to go to nitrogen, to moles of nitrogen. And then from moles of nitrogen, we want to go to volume. Okay, now with this, I'll just use the molar volume method. So the molar volume, I need RT, so I need the temperature and I need the pressure, RT over P. And so I can calculate the molar volume under these conditions here. Let's see. So they calculate the molar volume under these conditions, and it's high pressure. So high pressure is going to compress that volume. Although high temperature will expand the volume, it looks like the pressure wins out. 248 atmospheres is very high. So the molar volume is very small, only 0.281 liters of gas per mole. And so we go from grams of ammonia to moles of ammonia using the molar mass. And then moles of ammonia to moles of nitrogen using the mole ratio in the equation here. It's a 1:2 mole ratio. And then moles straight to liters of gas using the molar volume which was just calculated here. So 75.6 liters of nitrogen gas. Okay, looking at when properly detonated, ammonium nitrate explodes violently, releasing hot gases. So this is ammonium nitrate. Here it's producing nitrous oxide and steam. If the total volume of gas produced, both dinitrogen oxide, dinitrogen monoxide, they're losing the mono there, but it's okay, and steam, is 82.3 liters. Ooh, this is tricky because that's the total volume of gas. How many grams of ammonium nitrate exploded? All right, and so there are multiple ways of solving this particular problem. One way is we know the volume fraction is equal to the mole fraction. And so when we look at this, there are multiple ways of solving this particular problem. And so one way is if we have a total volume of 82.3, then 1/3 of that volume is N2O, and 2/3 of that volume is H2O. And that's because, you know, this whole thing has to add up to this. And so one way we could do this is we form a mixture, and we have the total volume of the mixture, and we're going to treat this as, we could treat this as Avogadros, for example. We could treat this as an Avogadros, or we could treat this as Dalton's. Either way, let's treat it as an Avogadros. Might be better. And so this is 82.3 liters of mixture, N2O and H2O. But for every N2O, I form 2 H2Os. So I get 2 parts of H2O for every 3 parts of total gas. And this is liters of total gas. And so if I want the volume of N2O, I could easily figure out, or if I want the volume of H2O, I could figure it out. And so this is going to equal the volume of N2O plus the volume of H2O if we do Avogadros, which we'll do. In stoichiometry, it's easiest just to do Avogadros. And so we have 2 unknowns here, but we also have 2 equations because it occurs in a 1-to-2 ratio. So we're always going to get twice as much. And so what we could do is we could just use the fractions here. And so the volume of N2O is equal to the volume fraction. That is 1 part of N2O. So we could just say 1 liter of N2O for every 3 liters of gas. So we have 3 parts here altogether. And so 1/3 of it will be, and so we have 82.3 liters. And so this is going to give us 82.3 divided by 3. It's 27.43. 27.43 liters of N2O. And the rest is H2O. Therefore, minus the 82.3, 54.86 liters of H2O. So it doesn't matter which one we pick. I'm going to pick the N2O. So what we're going to go is we're going to go from liters of N2O to moles of N2O using the molar volume here. So I need to calculate the molar volume under these conditions here. And then from moles of N2O, I'm going to go to what are they saying here? How many grams of ammonium nitrate? So moles of N2O to moles of ammonium nitrate, and moles of ammonium nitrate to grams of ammonium nitrate. All right, there are multiple methods, like I said. So this is method number 1. Method number 2, we could do it like this. Ideal gas law doesn't care what the gas is. And so what we could do is we could do 82.3 liters like this. And then we could go to moles of gas mixture. This is liters of mixture. This is not pure. And then we have a mole ratio times this. How many moles of gas total? So 1 mole plus 2 moles gives us 3 moles of gas total. in this mixture. And so the mole ratio here is 1 mole of ammonium nitrate gives us a total of 3 moles of gas, total gas. So for every mole of ammonium nitrate that decomposes, we're going to generate 3 moles of gas here total. And then from there, we can get grams of ammonium nitrate by using the molar mass. And there are more methods we could use, but you know, when we're dealing with a mixture, these are 2 common ways of doing it. One, figure out, you know, how much of each component we have, which I'm doing on the top. 2, just forget about figuring out how much and just total up the stoichiometry, being 3 moles of gas total produced for every 1 ammonium nitrate that decomposes. So let's see what the book did. The book used this generic. What they did was they used this generic conversion factor. That is, they said for every mole of ammonium nitrate, 3 total moles of gas decompose. So they calculated the molar volume here, and they just used the total mixture. They didn't separate it into the components like I did in method 1. They just took it, and then they know that for every 1 mole of ammonium nitrate, we get 3 moles of gas, and we can figure out how many total moles of gas we have based on the volume, because, you know, the volumes are additive in Avogadro's law. You know, the bigger the volume, the more moles; the smaller the volume, the fewer moles. So it's additive, and so they go from liters of total gas to moles of total gas, moles of total gas to moles of ammonium nitrate, and then to grams of ammonium nitrate. So they use method 2 here. So this number 39, I mean, what was that, number 29? Still, number 39 was, that's a tough problem, I guess. That should be in the challenge section, probably, number 39. This is weird. I'm going in circles. We already did pyrite. I don't know why I'm back at pyrite. And we just did this problem. Okay, there, 41. Sulfur burns to SO2. Actually, I'm almost out of time. With a beautiful deep blue purple flame, but with a foul suffocating odor. How many liters of O2 are needed to form 35.2 liters of SO2? This is the easiest type of stoichiometry to do. The easiest type of stoichiometry to do is when we're going from gas to gas. If we're going from gas to gas under the same conditions, then we can use a volume to volume conversion factor. And so let me tell you what I mean by that. Actually, we're out of time. But sulfur solid plus O2 gas yields SO2 gas. So it's a 1 to 1 to 1 mole ratio. The mole ratio is always true, but it's also a 1 to 1 to 1 volume ratio. The volume ratio is true if the pressure doesn't change. And it's also 1 to 1 to 1 pressure ratio. So when I read this equation, I read it in 3 ways. 1 mole of sulfur, 1 mole of O2, 1 mole of SO2. Well, sulfur is not a gas, sorry, so we can't do volume. These are gases. So 1 liter of O2 will produce 1 liter of SO2, or 1 atmosphere of O2 will produce 1 atmosphere of SO2. So we can do it that way as well. But I'm out of time, so we'll come back to this one, 41A, tomorrow, and then we'll look at that. And so I posted the link for Canvas. You can upload it. Again, that's a group quiz for that. And then the exam 2, turn it in by tomorrow morning, you know, like 9 a.m. or so tomorrow morning, 10 a.m. tomorrow morning, okay? Any questions before we end things here? Yeah, just turn it in before class tomorrow, the exam. A hint on number 32, just keep working on that dimensional analysis. Just keep trying to get the units to cancel out, and make sure you don't make up some weird conversion factors. you know, just use your standard conversion factors that we've been using. And you're going to have to look up some masses, you know, some molar masses or some, yeah, you're going to have to look up some molar masses or some atomic masses or isotopic masses. But those, go back in the PowerPoints. Those should be in the PowerPoints, I think. Plus they're natural abundant. Well, natural abundance you don't have to look up because I gave that to you. All right. If there are no other questions, we're going to wrap things up here. Yeah. Okay, thanks. We'll see you guys tomorrow. Bye now.